All right. We are going to do these derivations for our tangential and normal components of acceleration. So our idea here, or what we came up with in class, is we came up with an expression for our acceleration vector. We came up with our tangential and normal components of acceleration. We said our acceleration was a derivative with respect to time of magnitude of our velocity times our unit tangent vector plus this quantity. We have this magnitude of our velocity times the magnitude of t prime times our unit normal vector. And we said this was our tangential component, a sub t, and this was our normal component, a sub n. And we want this a sub t and a sub n in terms of r prime, and r double prime. And we're going to accomplish this by looking at v dot a, v cross a, and a dot a to come up with those expressions that we talked about in class. All right, so let's start with v dot a. Now, in order to get to the expressions that we want, we're going to express our velocity, and we talked about this in class as well, as the magnitude of the velocity, our speed, times our unit tangent vector. So we have our magnitude and our direction here. And we're going to use this quantity for our acceleration to perform these operations with. So v dot a is going to be the magnitude of v times our unit tangent vector, and we're going to dot that with our acceleration. Derivative with respect to time of the magnitude of v times our unit tangent vector plus magnitude of v, magnitude of t prime, times our unit normal vector. Now we're going to do this dot product. So we get, for our first term, we get v, magnitude of v, times the derivative of the magnitude of v, and we get a t dot t here. Plus, and for the second term, we're going to get a magnitude of v squared times this magnitude of t prime times t dot n. Well, t and n both have magnitude 1. So, and we know that t dot t is its magnitude squared, so t dot t is 1. And t and n are orthogonal, so t dot n is 0. So then this last term goes away, and we get that v dot a is equal to the magnitude of our velocity times the derivative with respect to time of the magnitude of velocity. And we know that a sub t is this quantity derivative with respect to time of the magnitude of velocity. So we can write that a sub t, this is our tangential component of acceleration, so a sub t is going to be the quantity v dot a over the magnitude of v. And if we write that in terms of our position vector, our acceleration vector, and our velocity vector, we get r prime dot r double prime over the magnitude of r prime. And that's the first of those quantities that we're looking for. We have our tangential component of acceleration in terms of our original vectors and its derivatives. Now let's look at v cross a. We're going to use the same quantities for our velocity and our acceleration as we did in the previous one. So we get the magnitude of v times our unit tangent vector, and we're going to cross that with our acceleration vector. So that's going to be the derivative with respect to time, magnitude of the velocity, times our unit tangent vector, plus magnitude of velocity, magnitude of t prime, times our unit normal vector. And now we're going to follow the same procedure. We're going to do this cross product. And if we look at this cross product, we might be able to start seeing ahead of time what's going to happen. So we're going to get magnitude of v times the derivative of the magnitude of v times t cross t. Plus, and again we get this quantity v squared magnitude of t prime, and then we get a t cross n. Well, t is parallel to itself, and we were looking for a scalar quantity, so we're going to end up looking at magnitudes. So we're going to look at the magnitudes of these cross products. T is parallel to itself, so the magnitude of t cross t is going to be 0. And since t and n are orthogonal, the magnitude of t cross n, which is the magnitude of t, magnitude of n times the sine of the angle between them, is going to be 1. So this time we get this first term dropping out, and we're left with the second term. So v cross a, and I'm going to do the magnitude of v cross a. These are already, we have magnitudes, so they're already scalars. So that's going to be, this first term goes away. We get the magnitude of v squared, magnitude of t prime, and that's our expression for the magnitude of v cross a. And we know that our tangential component of acceleration is the magnitude of v times the magnitude of t prime. So we can write divide both sides of this by the magnitude of v, we get that a sub t is the magnitude of v cross a divided by the magnitude of v. And in terms of our position, velocity, and acceleration, it's going to be the magnitude of r prime cross the magnitude of r double prime over the magnitude of r prime. And this is the second of the quantities that we were looking for. Our tangential component of acceleration, and this shouldn't be a sub t, this should be a sub n. Sorry. Our normal component of acceleration, that's what we were looking for. We already found our a sub t. A sub n is v cross a over the magnitude of v, and that's r prime cross r double prime over the magnitude of r prime. All right, finally, let's look at a dot a. And we know that that is the magnitude of a squared. And here we can just write, I'm going to write this as a sub t times unit tangent vector plus a sub n times the unit normal vector. And we're going to dot that with a sub t, t plus a sub n, n. And we're going to do this dot product. So we get a sub t squared, t dot t, plus, and we get two of these a sub t, a sub n, t dot n's. And then finally we get a plus an a sub n squared, n dot n. And we know that t dot t equals n dot n. Both of those are 1. And since t and n are orthogonal, t dot n is 0. So we can say that the magnitude of our acceleration squared is a sub t squared plus a sub n squared. And we solve this for a sub n, get a nicer way to find our normal component of acceleration. We can say that's the square root of the magnitude of a squared minus a sub t, tangential component of acceleration squared. And that's the third of those quantities that we were looking for. And these are going to make our lives much easier when we're working on problems that involve tangential and normal components of acceleration.